Hi there, and welcome to Module 3, presentation number 2 of Laser Classroom, Bringing STEM to Light, in which we will begin to explore the phenomenon of color. We'll do some exploring and some explaining, and we'll go back and forth between the two of those things, and we'll set ourselves up for a really fun, elaborate activity that we'll do in the next presentation, presentation 3. So, exploring and explaining color. Color is really fun. It's super engaging, and it's really familiar. But there's an awful lot of complicated information when you start really thinking about color. So we know that light comes from a source and it bounces off of objects into our eyes, and that's how we see. But if you look around, most of the light that we are experiencing in our everyday lives is white light, or what some kids will call clear light. That's kind of the experience of the light that's around us. We don't experience the light as a color, we just kind of experience it as transparent. And yet this clear or white light, if that white light is bouncing off of everything, then how in the world are we getting all these different colors around us? Where are they coming from? Well, remember the dress phenomenon, in which many people saw this dress as blue and black, and many other people saw it as gold and white. There is nothing like a phenomenon like that to remind us that color is a human perception. It isn't an intrinsic property of things. It's a perception of wavelengths that happens in our brain. One of the supplemental videos for this module goes into great depth to that kind of timeless question. Are you seeing red the same way I'm seeing red? I'd encourage you, when you're done with this, to take a look at that and watch that video. So light's all we see, and if the light is coming in that's white, how do we see so many colors? And it's how do we get all the perception of all those different colors in our brains? Well, it turns out that white light actually has all the different colors in it. Every single ray of white light has a hidden rainbow inside, and we're going to use the diffraction grating to unlock that rainbow and get a look at that rainbow. So if you hold this diffraction grating up to your eye and look up at a white light, never the sun, but any other white light, a light in the room or a bulb. It works best if it's a small source of light. So you'll see rainbows if you look at the window also, but the smaller the point of light, the better this is going to work. And if you don't have the kit, if you're looking for where to get a diffraction grating, in the materials section, it describes where you can get these diffraction gratings for very inexpensive at a company called Rainbow Symphony, and their website is rainbowsymphony.com. So if you look up at the light with your diffraction grating, you'll notice that there's a spectrum to the left and to the right of the point of white light in the middle. And we're going to ask kids to use some crayons or some colored pencils and draw a picture of what they see. And we're going to ask them to record their observations along with answers to a couple of questions. How many colors can you find? Can you identify red, yellow, green, blue, purple, orange, violet? How many colors do you see? And what do you call them? And then what color is closest to the light? And what color is furthest away? And if you look at different lights, are the colors always in the same order? Well, it turns out they are. It turns out they are always in the same order. So we know now that white light is actually made up of a whole bunch of colors. So what's happening with that diffraction grating? Well, when light passes through the diffraction grating, the grating is made up of a whole bunch of teeny little lines spaced very, very closely together. And the different frequencies of light that are in the white light actually bend at slightly different angles when they pass through that grating. So it causes each frequency of light or each wavelength or color of light to bend at a slightly different angle. So all the red is going to bend this much, and all the yellow is going to bend this much, and then all the green is going to bend this much, and you're going to be able to see it kind of fan those colors out around the room. So it literally separates the different wavelengths out of the white light. So they're all still there, it just separates them out so you can see them. So now we know that white light is composed of many different colors. Well, really? It's actually still a bit abstract. I'm looking at the white light, I'm seeing the rainbow, but in third grade, I do not understand diffraction. That is not going to make a whole lot of sense to me. And so I'm still kind of at the point of having to take your word for it, that white light is really made up of all those different colors. Well, let's make that concept a little bit more concrete by putting these lights, either these light blocks or other LEDs, or if you don't have colored LEDs, you can even put cellophane over a flashlight and create red, blue, and green. But what you're going to need is a really good filter, or a really good piece of cellophane that makes that light a nice pure blue and a nice pure red and a nice pure green, so that you can get the colors that we really want to see here. And so we're going to mix these colors, and we're going to have a little bit of guidance for how to explore how to do some color mixing here with these lights. And we're going to mix red and blue, and red and green and blue, and then finally put the red, the green, and the blue together and adjust how close and how far away from each other they are, and how much red and how much green and how much blue, and see if you can make a nice pure white light. It's really, really cool to be able to actually see it and have that hands-on experience of doing that. At this point, if you wanted to go into wavelengths of light, if you wanted to go into the electromagnetic spectrum, if you wanted to do some explaining in that arena, this would be a good time to do that. We did that in Module 1. We talked about how the wavelength and the frequency determines not only the color, but also the kind of light, right? So everything between 700 and 400 nanometers is visible, and depending on what wavelength within that visible range is going to give you a specific color. There's actually hundreds and hundreds of different colors inside of that. We just can't see all of them. We can't distinguish all of them. We can't see the difference between 700 and 702 nanometers. Our eyes just aren't that sensitive. But then there's all this other light that is, it's still light, but it's simply not visible. We can detect it and experience its impact in other ways. So this is a good time to go into that if that is something that you're going to do. However, did you notice that when you combined the red light with the green light, you got yellow? And if you have any experience with mixing paint, or the kids have experience with coloring or ink or dye of any kind, you know that when you mix red and green paint, you do not get yellow. You get kind of a muddy mess. Why is that? Why would it be different for light than it is for paint? Well, it turns out that light is not anything like paint, right? So we're seeing, so when we see light, we're actually seeing the light. But when we see an object in white light, we're seeing only the wavelengths that are reflected back to us. So light is not like an object, right? Light is this electromagnetic wave. It's this subatomic particle that is massless and traveling at this amazing speed. So it makes sense that it wouldn't behave exactly the same way that materials behave. So what's happening with light is when you add two frequencies or wavelengths of light to each other, those two wavelengths or frequencies combine with each other, and they produce a different wavelength or frequency of light, which we perceive as a different color. And so when you add red to green, you get yellow. When you add red to blue, you get this nice magenta color. Some might want to call that pink. But when you think about pink light, be sure to check out the supplemental video on pink, the color that doesn't exist. Take a look at it. When you combine green and blue, you get this nice cyan. And when you put them all together, all those wavelengths all combine together to produce this experience of white light. And that's additive color mixing. What happens with materials or subtractive color mixing is that the way we see those is, so this white light comes into a material, right? Now, white light from our white light bulb hits something red. All the wavelengths or colors of light in that white light are absorbed by that red material, except for red. The only wavelength of light that's reflected back to our eyes, and remember, all we can see is light that's reflected back to our eyes. So if this wavelength that's being reflected back to our eyes is red, we're going to experience that as red. And that's why we see red. Same true for something green. If it's green, it's going to absorb everything except for green and emit only green. Now, the reason you get a muddy color when you mix red paint with green paint is because the red paint is absorbing all the colors except for red, and the green paint is now absorbing all the colors except for green. And so instead of getting an additive effect of more light being reflected back to your eyes, now less light is being reflected back to your eyes, because that red plus that green are going to subtract colors out of what's getting reflected back to our eyes. So we're not going to see as much color, and it's going to look kind of brown or muddy instead of nice and bright and white the way light does. So that's light. I will see you in the next presentation where we will go into an elaborate activity. We're going to use everything that we've just learned about color to try and sort some M&Ms in the dark. See you then.